In the realm of machine learning, classification reigns supreme as a fundamental task within supervised learning. It is one of the most essential techniques that data scientists and machine learning practitioners rely on. Its essence lies in the art of training algorithms on labeled data, empowering them to accurately categorize new, unseen instances into predefined classes. This process is crucial for making sense of vast amounts of data. Imagine a scenario where you aim to predict whether an email is spam or not, or perhaps discern fraudulent transactions from legitimate ones. These are prime examples where classification algorithms take center stage. They help in automating decisions that would otherwise require human intervention. At its core, classification involves learning a mapping function from input features to discrete output labels. This mapping function is what allows the algorithm to make predictions on new data. These labels could represent anything from different animal species to various medical conditions. The versatility of the classification makes it applicable in numerous fields. The beauty of classification lies in its ability to transform raw data into meaningful insights, enabling us to make informed decisions and predictions. This transformation is what drives innovation and efficiency in many industries. The importance of classification in today's data-driven world cannot be overstated. It is a cornerstone of modern data analysis and decision-making processes. From image recognition and natural language processing to medical diagnosis and financial modeling, classification algorithms are ubiquitous, underpinning countless applications that shape our lives. They are integral to the functionality of many systems we use daily. As we delve deeper into the world of classification, we will explore three prominent algorithms: logistic regression, decision trees, and support vector machines. Each of these algorithms has its own unique characteristics and use cases. Each algorithm offers a unique approach to solving classification problems, and understanding their strengths and weaknesses is crucial for selecting the most appropriate method for a given task. This knowledge is key to optimizing performance and achieving the best results. Logistic regression, despite its name, is a powerful algorithm designed for binary classification tasks. It is one of the most fundamental and widely used techniques in the field of machine learning. Unlike linear regression, which predicts continuous values, logistic regression outputs the probability of an instance belonging to a specific class. This makes it particularly useful for classification problems where the outcome is categorical. This probabilistic approach makes it particularly well suited for problems where understanding the likelihood of an outcome is crucial. It allows us to make informed decisions based on the predicted probabilities. At the heart of logistic regression lies the logistic function, also known as the sigmoid function. This function is essential for transforming linear outputs into probabilities. This S-shaped function takes any real-valued input and squashes it between 0 and 1, representing the probability of the positive class. It ensures that the output is always within a valid probability range. By applying the logistic function to a linear combination of input features, we obtain a probability score that dictates the predicted class label. This score helps in making binary decisions. One of the key advantages of logistic regression is its interpretability. It allows us to understand the relationship between the input features and the predicted outcome. The coefficients associated with each feature provide insights into the factors influencing the classification decision. This makes it easier to explain the model's predictions. For instance, in spam detection, a large positive coefficient for the word free might indicate a higher likelihood of spam. This helps in identifying key indicators of spam emails. Logistic regression is widely used in various domains, including medical diagnosis, credit scoring, and marketing analytics. Its versatility makes it applicable to many different fields. Its simplicity, efficiency, and ability to provide probability estimates make it a valuable tool for a wide range of classification problems. Logistic regression continues to be a cornerstone in the toolkit of data scientists and analysts. Decision trees, as their name suggests, employ a tree-like structure to make classification decisions, mimicking the way humans make choices. They partition the data into smaller and smaller subsets based on a series of questions or rules, each step narrowing down the possibilities. Ultimately, this process leads to a leaf node representing the predicted class label, which is the final decision. The process of building a decision tree involves recursively splitting the data based on the feature that results in the most homogeneous subsets, ensuring the most accurate predictions. This homogeneity is typically measured using metrics like information gain or Gini impurity, which are crucial for evaluating the quality of each split. These metrics quantify the reduction in uncertainty achieved by the split, helping to refine the decision-making process. Decision trees offer several advantages, including their ease of interpretation and ability to handle both categorical and numerical data, making them versatile tools in data science. Their hierarchical structure provides a transparent view of the decision-making process, making it easy to understand the factors driving the classification, which is valuable for stakeholders. However, decision trees can be prone to overfitting, especially when dealing with complex datasets, where the model becomes too tailored to the training data. This occurs when the tree becomes too specific to the training data, resulting in poor generalization performance on unseen instances, which can be problematic. Techniques like pruning and ensemble methods can help mitigate overfitting and improve the model's robustness, ensuring better performance on new data. Support vector machines, or SVMs, are powerful algorithms known for their ability to find optimal decision boundaries between classes. Unlike other algorithms that aim to minimize overall error, SVMs focus on maximizing the margin, which is the distance between the decision boundary and the closest data points from each class. The data points closest to the decision boundary are called support vectors, as they play a crucial role in defining the margin and the orientation of these hyperplane. SVMs aim to find the hyperplane that maximizes this margin, leading to better generalization performance. One of the key advantages of SVMs is their ability to handle high-dimensional data and nonlinear decision boundaries through the use of kernel functions. These functions map the data into a higher dimensional space, where it may be easier to find a linear separating hyperplane. SVMs are widely used in various applications, including image classification, text categorization, and bioinformatics. Their ability to handle complex data sets and achieve high accuracy makes them a popular choice for many challenging classification tasks.